Okay, let's get started. Okay. So last time we started talking about gradient descent, and we particularly covered it in the context of what does it mean for gradient descent to converge, and what does it take for gradient descent to converge in the specific example of the least squares problem, right? And there we saw fundamentally that a key quantity that is relevant are the eigenvalues of the matrix A transpose A, right? And specifically, your step size has to be chosen in accordance with those eigenvalues such that you can make sure that that specific quantity, right, identity minus eta A transpose A, or 2 eta A transpose A, always has eigenvalues less than 1, right? Everyone remember that we talked about last time? And the special thing about that matrix, right, the matrix that we had was that this is a symmetric matrix, right? So identity is symmetric, A transpose A is symmetric, so this whole thing is a symmetric matrix, so we can easily understand its behavior based on its eigenvalues. And in particular, you can easily extract the eigenvalues of this thing based on the eigenvalues of A transpose A, right? Because using the shift property of eigenvalues, you're going to have this basically to be 1 minus 2 eta times whatever eigenvalue of A transpose A is going to be the eigenvalue of this other matrix, right? And so you wanted the absolute value of these eigenvalues to be less than 1 for convergence. Okay? But of course, not every problem is least squares, right? And we kind of already had a solution for least squares. We had a formula. We saw at the end of last class that sometimes gradient descent can actually be more efficient and faster than actually doing the inversion of A transpose A. However, it would be really nice if we could use gradient descent for something other than least squares, right? Making all of this effort to just solve, yet again, least squares in another way doesn't seem like the best use of our time. And turns out gradient descent is indeed useful for many, many things. And in fact, gradient descent is used in the context not just of convex problems, but also for non-convex problems, right? So we know that if our problem is convex, then gradient descent will stop when gradient of f is equal to 0. And when it stops, you know that this will be a minimum, right? But the question is, can we say anything beyond convex functions, right? Convex functions are great, but we have a lot of non-convex things. And in particular, what happens if you have some function that is non-convex that is maybe of this form, where I have some, it's like super wigglies, something like this, right? How do I know what gradient descent is going to do? And well, you know, depending on where you start gradient descent on the function like this, you can end up in lots of different places. For example, if you started gradient descent here, depending on your step size, you might converge to something like this, right? If you started here, you might converge here. If you started here, you might converge here. And so for a non-convex problem, gradient descent can get stuck in lots of local minimums. And so there are different techniques that you will use to kind of extricate gradient descent out of these local minimums to try and get to a global minimum, or try to get better performance. And today we're going to talk about one of those, which is stochastic gradient descent. But before that, I want to generalize our proof for least squares and just talk a little bit more about the case of convexity. And I want to talk about gradient descent for smooth and strongly convex functions. Okay? What are these smooth and strongly convex functions? Well, we've only analyzed gradient descent for this kind of one special case of these squares. What we're going to do is we're going to generalize this analysis to talk about cases that are basically like quadratics, right? Convex quadratics are basically our best bet. Those are the things that are the nicest. Least squares is one of them. But can we generalize to beyond this? So what a smooth and strongly convex function is it's a function that is basically going to be sandwiched by quadratics. It's a function that has a lower bound that is given by a quadratic, as well as an upper bound that is given by a quadratic. So when I say a function is mu strongly convex, what I mean is that if I have some f of x prime, then this is greater than or equal to f of x plus the gradient of f of x, x prime minus x, plus mu over 2 x prime minus x whole square. Okay? So what is this saying? What does this expression here on the right-hand side look like to you? Or this, in general, this inequality. This looks very similar to kind of the Taylor expansion that we write out, right? I have an f of x here, and then it's equal to something. Then there's the gradient. Oh, sorry, there should be a transpose here. Times, the perturbation that you have. And then there's something that looks like a quadratic term. Does everyone see the similarity to the Taylor expansion? Yes? No? Thumbs up? Okay, good. So what this is saying that, look, I want to be in a situation where my gradient is not changing too slowly, okay? And why do I say that? When I say I want f of x to be greater than or equal to this, right? If I wanted to write out just the Taylor series of this, I would have an approximately equal to here. And instead of this term here, what would I have? I would have x prime minus x times the Hessian times x prime minus x, right? Or x prime minus x prime minus x transpose times the Hessian times x prime minus x, right? Does everyone see that? That would be the term that I would get for the Taylor series. So this is saying that if I look at that Hessian and I look at the eigenvalues of that Hessian, I want them all to be basically greater than or equal to mu, right? I want the eigenvalues to be largish of that Hessian. And by saying that those eigenvalues are largish, I'm saying that the gradient is not changing too slowly, because the Hessian is what is telling me how fast my gradient is changing. Right? Does everyone see that? Yes? No? Questions? Yes? Mu, this is a Greek letter mu. Mu. This just is a constant belonging to R. It's a real number. Other questions? Yes?
Why is it bad if our gradient changes too slowly?
Why is it bad if our gradient is not, so why is it bad if our gradient changes slowly, right? So let's say you have some function like this, and this gradient is kind of, there's a gradient, but it's basically almost constant, or it's not changing very much at all, right? What does that mean? That means that you're not going to be making progress, right? You're going to be going super slowly towards wherever your minimum is. And what we want to be able to do is we want to be able to prove convergence. And so by saying your gradient is not changing too slowly, you're able to say that, look, I can give you some guarantee of the rate at which you will make progress. Okay? Like if you're just not moving, if somehow your gradient descent algorithm is such that it keeps like xk is here, and xk plus 1 is here, and xk plus 2 is here, and xk plus 3 is here, you're just somehow not moving very much, then maybe you'll never converge. Right? And what we want to say is we want to have guarantees about when we'll converge. That's why you want to guarantee that there'll be something will happen every time you take a step. That's a good question. Does that make sense to everyone? Why is a slow gradient, slowly changing gradient, a bad idea? Can I repeat the thing about the quadratics? Okay, so everyone sees that this is like Taylor's theorem, right? What is the term here when I write out Taylor's theorem? I have, okay, let me just write this over here. So what does Taylor say? Right? This is what Taylor says. Okay? So you see here that the first two terms are identical, right? So now think of this as x prime. Then this thing is x prime minus x. Right? So now what you have is that you're saying, I want to just, the only difference is in this last term here. And instead of approximately equal, I want to say I want to be greater than or equal to this. So I will be greater than or equal to this if my Hessian term is greater than or equal to this term, right? Which I can say by saying that my eigenvalues of my Hessian are basically greater than or equal to mu. Does that make sense to everyone? So I want to have my Hessian have eigenvalues that are not too small. They're at least mu. Lambda is the scaling of that quantity, right? You have the same thing here, so there's no issue there.
Oh, okay, sorry.
Now, similarly, when you're trying to get to convergence, you can see the issue of not moving at all, right? That's an issue that you've all agreed is a problem. What's the other issue that you might have, or that we saw when we were looking at gradient descent? You might just move way too much, right? You might like just jump completely to a different spot. You might completely overshoot the minimum. All of this is also extremely bad. So you also want to make sure that your function is not changing too fast, right? So for that, I'm going to define what is called L smooth. And here I have f of x prime less than or equal to f of x One thing I forgot to say explicitly before I get to L smooth is, of course, being mu strongly convex implies that you're convex, right? Remember, for being convex, all you need to make sure is that your Hessian is positive semi-definite, right? If your eigenvalues are not just greater than 0, but they're greater than some mu that is strictly greater than 0, I should add here that we always choose mu strictly greater than 0, then of course it's convex, right? So strong convexity always implies convexity. Okay? Good. So now coming to L smooth. This is basically the same thing, but with the inequality flipped. I don't want things to change too fast, okay? So and now if I have a function that is both mu strongly convex and L smooth, I basically have a quadratic sandwich, right? I have an upper bound by a quadratic of my function, and I have a lower bound of my function that's a quadratic. And so even if my function isn't itself a quadratic, I have strong reason to believe that it will behave like a quadratic, because it's sandwiched on the top and the bottom by something that is a quadratic. Make sense to everyone? Yes? No? Question? Question? Yeah, question? No. This is an upper bound and this is a lower bound. These are distinctly different.
Can you explain what does it mean to be like quadratic?
That is just that's all I mean. I mean nothing more than that it's like a quadratic. Okay, are we good with this? Yes, question. Why is it called L smooth? I do not know where that term came from. It's just the term. Yeah, it's just the standard terminology. I'm sure there might be alternative terminologies in other communities as well. So what we want to do now is we want to be able to prove a theorem that says for functions that satisfy this, gradient descent will converge to a minimum. Okay? And to do this, first I want to prove a lemma. Okay? So if f is L smooth, then the gradient of f of x is less than or equal to 2L times f of x minus f of x star. Okay, x star is okay, so let's say you have x star, which is your minimum point, or is the argument that achieves the minimum. Then, basically what I want to say is that the gradient at x, at some point x, is always upper bounded by this constant L times my distance from my minimum, right? So if I'm further away from my minimum, my gradient is allowed to be larger. If I'm very close to my minimum, my gradient has to be smaller, right? So this is the thing that is pushing us towards convergence, right? It's saying my gradient is not changing too fast, right? So L smoothness implies this condition, okay? So that's what we want to now try and prove, okay? So why don't you take a minute to just like think about how you might do this before we all do it together. So this is like, it's not quite obvious, I mean, to go from this to this. This doesn't come by just a manipulation of this expression, right? First, because one of the things we want to pull in is we want to pull in this x star, right? And we need to kind of figure out how to pull that in, right? So we want to be able to try and think about that, okay? So the way I'm going to do this proof is I'm going to consider two different points. I'm going to consider my vector x, and I'm going to consider vector x minus 1 over L gradient of f of x. So kind of like I'm at x, And let's say I take a gradient step from x to this point 1 over L gradient f of x, right? So I'm moving in the gradient descent direction. And my step size I'm choosing is 1 over L. And you'll see why I'm choosing this 1 over L eventually. But I know now if x star is a minimum, what do I know? If I know that f of x star had better be less than or equal to f of x, right? It's the smallest. F of x star had also better be less than or equal to f of x minus 1 over L gradient of f of x, right? Both of these things had better be true. So now here I have something that's kind of the difference between two things, right? I want to be able to pull in somehow my L smoothness definition here. So can I think of this as kind of x plus delta x, right? And apply this L smoothness definition here? Yeah? So what happens? Can you apply this? So if I write f of now x minus 1 over L okay? So think of this as now x prime in that definition over there and apply that definition. What can you write this as upper bounded by? What is this upper bounded by? It's a good exercise to make sure you can just map things from one to the other. No, I'm not asking you to figure out what fx is. I'm literally just asking you to substitute. I just want you to write this thing out. I just want you to write the bound out. So x prime is equal to that quantity now. So what is x prime minus x? So what's the first term here? What's the first term in the bound? I'm just applying the definition of L smoothness. Yeah, fx, right? Okay, good. Plus, what's the second term? Gradient of f of x transpose times what? The difference between these things, right? What is the difference? Minus 1 over L gradient of f of x, right? Remember, I have an x prime minus x over there. So I'm going to carry, I have this minus sign here, right? And then what's the third term? Plus, now I get an L over 2. And what's the difference between x prime and x is now, again, exactly this. So norm squared of minus L gradient of f of x. Right? Everyone got this? Okay. This is equal to f of x plus, well, not really, and now I can say minus 1 over L. And I have gradient of f of x transpose times gradient of f of x. What is that equal to? The norm squared, right? And what do I get here? I get L over 2, and I get 1 over L squared. So I get 1 over 2L which gives me right? One of the L's cancels, basically. Okay, so now what does this get you? Are you almost basically done? Right? Because now this gives me the fact, this implies that f of x star is less than or equal to f of x minus 1 over 2L gradient of f of x, which just rearranging gives me what I want. Okay? So f of x star is a minimum. This is some generic point. Which one has to be smaller? How do we know that the second point we're using is in the domain of f? Great question. Here I'm assuming that basically we're doing an unconstrained optimization. So my domain is all of Rn. If I have time, I'll teach you about projected gradient descent, where we can talk about when a gradient step might take you outside the domain. But we're not there yet. Okay, we're good? Everyone on top of this lemma? Okay, now we can use it. So now what we want to be able to do is we want to be able to prove that basically we're converging eventually to our minimum, right? So we want to be able to prove something of the form theorem right? If f is both mu strongly convex and L smooth, I want to be able to show that eventually, as t goes to infinity, gradient descent will converge me, the iterates of gradient descent will converge to the x star, right? So let's remind ourselves, how does gradient descent work? Right? This is an eta, this is a mu, right? These are two different Greek letters, don't confuse them. Right? The eta looks more like an N, the mu looks more like a U. Both of them have tails. But this is our gradient descent update, right? Everyone remember this? Eta is our step size. This thing is called eta. Okay. So one more thing that I want to write. Do I want to write this out now or later? Okay, I'll just wait. Let's keep going. I'll write it when I need it. Okay. So, proof. Okay, so let's now consider okay. Now I know that I'm using gradient descent. So what is the first substitution I might want to do in this thing to kind of pull in the fact that I'm using the gradient descent algorithm? I want to write xt plus 1 in terms of the previous point, right? Just so that I can remember what I'm doing. So I'm going to write this as xt minus okay? And now what do I want to do? What do I ideally want to be able to say? I have xt plus 1 minus x star, right? If I want to prove that this is converging to 0 over time as t goes to infinity, what quantity would I want to be able to compare it to? What's the natural thing I would want to compare it to? I want to say I'm doing better than I did in the previous time step, right? So I want to compare it to the distance that I was from x star in the previous time step. Right? I want to compare it to xt minus x star. So can I pull that out of this expression somehow? Right? I essentially kind of have this already here. So if I group these two things together, can I further write this, let's say, as xt minus x star, or x star norm squared, right? And then plus, I have a second term. So I'm expanding the quadratic. And what would that term be? This will become eta squared gradient of f of xt norm squared. And now what remains? If I have a quadratic, how do I expand it? What's remaining here? The cross term, right? Yes? Everyone is like totally asleep? Is the rain? What's going on? Okay, let's take like a 1 minute stand up and dance break. I want everyone to wake up. Take 1 minute and talk to your neighbor about something nonsense. But I need everyone to be awake for this proof. Because there's a term missing here, but you're all like not. There's one more thing to write. Yeah, there's one more thing here. No. Okay, that's 1 minute. Okay, let's come back together. Everyone awake? Feeling better? Okay, let's do this now. We want to compare xt plus 1. We want to compare the distance at time t plus 1 to the distance at time t, right? Somehow I keep putting the star at the bottom at the top. I keep confusing. But if it, like, x star with the star subscript is the same as x star with the star superscript. I'm sorry that I somehow keep changing where I put it. But I mean to say the same thing every time. Okay. Good. So now when I have something, I have some a minus b whole squared, right? It's a squared plus b squared minus 2ab. So now what's the term that's missing here? What's the term that's missing? 2 times inner product between xt minus x star and what? Eta gradient of f of xt. Right? Just quadratic formula, whatever, something. You've seen this before. Okay. So now, is there an inequality that we spent some time deriving that might be useful? So I want to keep proving. Now, do I want to prove an upper bound on this or a lower bound on this? Do I want to say that this is less than or equal to something or greater than or equal to something? I want to show that this is small, right? So I want to show that this is less than or equal to something. So I want to say that this is less than or equal to something. So what's the inequality that we just spent some time proving that would be useful to use? We have this term here. We just proved a lemma about it, right? So we can use our L smoothness. So this is xt minus x star plus eta squared times 2L times now f of xt minus So now we have this thing here. What can we say about this? What is the thing that we haven't used yet? We haven't used the mu strong convexity part yet, right? So what is this term? If I have minus 2 eta, and this is basically xt minus x star right? That term is just that term. Just writing the inner product, which is equal to minus 2 eta. I can write it as gradient of f of x transpose xt minus x star. Yeah? So how does this connect to the mu strongly convex definition, and how can you pull that in? How can you use that now? So do you see something with a term that looks like this in the mu strongly convex definition? Okay, so take a minute and try to manipulate this to get a bound on this. So use the mu strongly convex definition and try to manipulate to get an upper bound on this. So what term is this like? This is like this term, right? Okay, and I want to say that this term, something less than or equal to, okay? So let me write my mu strongly convex definition for f of x star now. Let me write f of x star is greater than or equal to f of xt plus gradient of f of x t x star minus xt plus mu over 2 x star minus xt, right? And now if I manipulate this, I get gradient of f of x t x star minus xt is less than or equal to f of x star minus f of xt minus mu over 2 x star minus xt. Right? I just moved things to one side. Moved this term, or I moved this term to this side, and I moved this term to this side. And so I get this thing is less than or equal to that, right? Yeah? Does that seem like a reasonable thing? Okay. And here I have minus 2 eta times this term. So this is exactly the same as this, right? Because these are opposite. What did I do here? Okay, there's nothing complicated that happened here, right? I just said, okay, this is f of x star minus f of xt minus mu times this is greater than or equal to this, right? This term. That's all that happened. Okay, this is just algebra. Like, don't get tripped up on the algebra. This is why I want you to write it down yourself and like do it out yourself, because you will not get tripped up if you do it out yourself. If you just copy it down, it's hard to understand, right? Okay, so now what can I use this to say? So let's make this even further precise. Therefore, minus f of xt transpose, and then I have xt minus x star, which is what I have there, is less than or equal to the same exact quantity. So now if I go from here, I can write this as less than or equal to I switch what sign?
Now the star is subscript.
Oh, sorry.
It's okay. You told me earlier, so I thought you might want to know.
Thank you. Good point. F of x star. And then now I can replace this with plus f of x star minus f of xt minus mu over 2 Oh, and we need a 2 eta, yes. Good point. So there should be, in front of all of this, there should be a 2 eta. No, I didn't do negative on both sides there. I just changed on one side. Yeah, it's x star minus xt is minus xt minus x star. Those two things are equal on the left-hand side. OK, so now are there terms that you would like to group together in this, right? What are the two kinds of terms here? There's an f of xt minus f of x star kind of term. And then there is an xt minus x star norm squared kind of term, right? So can we pull these together? So what is the coefficient in front of xt minus x star? Well, I have a 1 from this term. And then here I have a minus 2 eta mu over 2. So I have here basically minus eta mu. Right? This is the coefficient here. And now plus, what is the coefficient in front of f of xt minus f of x star? Well, from here I have a 2 eta squared L. And then from here I have a minus 2 eta. Right? So this is just equal to this. I've just grouped standard terms or terms that are like each other next to each other. OK? Good. So what did we start out wanting to try to do here? We said we wanted to compare this quantity to this distance from the optimum at the previous time step, right? OK? And have we done that? Kind of, right? Like here we have this comparison here. And then we have this other stuff here, right? Now, if I wanted to do convergence, what did we do in the least squares case to get convergence? We basically tried to get something such that xt minus optimum is some constant times xt minus 1 minus optimum, right? The distance from the optimum at a time t minus 1 multiplied by something gives me the distance from the optimum at the next time step, right? Remember that? And then I can just do recursion over and over and over again, and then get an exponent. And then that exponent, I can say if that exponent is less than 1, then that exponent must decay to 0. Right? Does everyone remember that that's what we did? So here we're like, well, here I have some exponent here, right? I have some kind of term here. But then I have this other stuff hanging around here. Okay? What would be really nice? What would be the ideal situation?
0.
Could I somehow make this 0 by magic?
Yes.
Wouldn't that be great? Great. How do you do it? So let's figure out what this magic is, right? It would be great if we could turn this to 0. What is the knob that we have that we haven't used yet? Remember, we're doing gradient descent. And what is the thing in least squares that it mattered how we chose? What was the key thing we had to choose correctly? The step size, eta. So what would you want to choose eta to be here? If I wanted to make this term 0, I could choose eta equal to, as someone said, 0, right? Would this second term become 0? Would you ever want to implement a gradient descent algorithm with eta equal to 0? No, right? So let's remove the 0 option. What is the next choice that you have? To make this 0, this is equal to 0 if eta equal to 1 over L, right? So if I choose eta equal to 1 over L, then I have 1 minus mu over L times xt minus x star whole squared. And now I'm basically almost done, right? So now I can do the same recursion. And so what do I get if I keep recursing this? This is now less than or equal to 1 minus mu over L to the t times x1 minus, or I can say t plus 1 and put an x naught here. And now, under what conditions is this thing going to converge to 0? As long as this thing is less than 1, I'm going to always converge to 0, right? And what do we know about 1 minus mu over L? Well, mu is basically the upper bound on the eigenvalues of the Hessian, right? Or sorry, mu is the lower bound. L is the upper bound, right? So mu over L is always going to be less than 1, right? So 1 minus mu over L is always going to be something with absolute value less than 1, which means that this thing is always going to converge to 0. How convenient. Okay? So this says that therefore this will converge to 0 as t goes to infinity, since mu over L is less than 1. Okay? So just to recap everything that we did, right? So we said that we have a strongly convex and L smooth function. And basically the idea is that, look, this is not quite least squares, but it essentially behaves in the same way as least squares, right? These properties are giving us this quadratic sandwich. And then what we've done here is all just manipulation. But if you can see, hopefully it's principled manipulation. It's not completely arbitrary. We've made choices, and we've made choices for a reason, intentionally. And you can see that now, by our definition of mu and L, and our choice of step size, we're always going to converge to 0. So we can generalize beyond just the least squares case. So mu and L are always positive, and so we're not worried about absolute values here. Why do we want this second term to be 0? Excellent question. I want this second term to be 0 because I want to basically be able to pull off this recursion step. And I want to be able to get this thing as an exponent. That's why. How do we know that mu over L is always less than 1? We know that mu is a lower bound on the eigenvalues of the Hessian. L is an upper bound on the eigenvalues of the Hessian. So the maximum eigenvalue is always bigger than the minimum eigenvalue, right? So mu over L is always going to be less than 1. How do we know that L is the upper bound? By the same exact logic that we know that kind of mu is the lower bound. So Remember we had this Taylor's theorem here, right? So this is approximately equal. On one side you're upper bounding this, on the other side you're lower bounding this exact term. Right? L smooth and mu strongly convex are kind of two sides of the same coin in that sense. Does that make sense? Okay, great. So now I want to move to, so this is just one example. There's many, many other cases. Like, for example, you can have, F, instead of having convex, strongly convex, you can prove similar results for convexity if you have some kind of Lipschitz condition on your function. You could prove different convergence rates. Here what we get is basically an exponential convergence. You can prove slower convergence rates for other situations. This is kind of the best convergence that you can get, this exponential convergence. Different convergence rates for different conditions. There's like a whole series of different ways you can do this. You can think of this lecture as a mini ad for 227C, where the entirety of the class is on, or not the entirety, but a large fraction of that class will be talking about different variations on gradient descent and convergence algorithms or optimization algorithms to try and understand, how they work, why they work, and what conditions you can improve them, what kind of convergence rates can you get. And these convergence rates really, really matter, right? Because this is telling you how long after you click run in your Jupyter notebook do you have to wait for, do you have that little black ball until you get an output, right? Can you run this on your MacBook or your Windows computer or whatever? That's the question. The faster you can run this, the more, the less computation you will need, right? So this is not just some exercise in pedantic linear algebra, right? It actually matters how fast these things run, and you want to know how fast they run so you can choose the right algorithm for the right situation. Okay? So that said, you might not always be able to get a gradient descent type algorithm to work, because gradient descent can be quite computationally expensive. So what I want to introduce you to next is the idea of stochastic gradient descent. So gradient descent says the following, right? Okay? And one of the expensive things in the gradient descent algorithm is computing this gradient itself. Right? Once you know the gradient, this addition is not so hard. But computing the gradient can sometimes be kind of expensive. Okay? And so stochastic gradient descent is one way of making that gradient computation a little bit faster and a little bit easier. Okay? So for example, if we have the least squares problem, right, then what we're looking to do is we're looking to minimize over x ax minus b whole squared, right? And let's say a belongs to this is kind of the way that we traditionally write the least squares problem. But my minimum is the same even if I write a divide by 1 over m over here, right? This doesn't change the solution. This is just a constant. I'm just dividing by the number of rows that they're going to be in A. Right? Let's say A is equal to something like this. These are all of the rows of A. Okay? Another way I can write this is min over x, 1 over m. I can write this row by row. I can take the sum of my residuals for every single row, or essentially every single data point that I have, right? I can write this as the sum of AI transpose times x minus bi. Right? This is just another way of writing that exact same thing. So if I could be lazy, and instead of trying to compute my whole gradient, is there kind of a shortcut thing that I might want to do? What I want to try and say is that instead of taking the gradient of this whole thing, I want to try and take the gradient just of this ith term. Okay? In general, let's say I have some f of x. And I can write this okay? So I'm taking what I have as my function and thinking of it as an additive loss. So typically, often in especially machine learning problems, what you have is a loss function or something that you're trying to minimize that is the sum of losses on many different data points, right? Or it's the sum of losses from many different cases. And instead of thinking about this function as this whole thing, I want to think about it as the sum of m different things. And if I was to be lazy about evaluating the gradient, what I can think about is I could say, instead of considering gradient of f of x, what if I just considered the gradient of fi of x? Okay? I have m different things. What if I just picked one? Okay? That's the basic key idea, in some sense, behind stochastic gradient descent. Is that can you just go on the descent direction that is given by a partial part of your loss, right? And you can see that, for example, in the least squares example, computing this gradient of fi of x is cheaper than computing the whole gradient, right? So the whole gradient here requires me to do a multiplication by an A transpose, right? But here, what is gradient of fi of x? Right? This is just equal to ai, or 2ai, times aix, ai transpose x, minus bi. Right? So instead of doing a matrix multiplication, now I just have a vector times a scalar, right? So it's much, much cheaper for me to compute this. Does everyone see that? So it's an easier thing to compute, basically because to compute my whole gradient, what would I have to do? I have to compute this for this term and this term and this, all of these different terms and average them, right? So I'm removing the computation of all of these other things. In fact, if I look at the expected value of the gradient of fi of x, in expectation, if I have m different choices, what is the expected value of this? In expectation, this is exactly equal to just the gradient of f of x. Right? So I'm choosing something. I'm choosing a random quantity, essentially, which on average is going to be exactly the gradient that I want. But it's kind of a noisier version of the gradient. It's not exactly the gradient. But in expectation, it's going the same direction that I want it to go. But it's easier for me to compute. So does everyone kind of see what I'm doing here? No, you don't. Ask me a question. This expectation is just, okay, so here, gradient of f of x is equal to what? So now if I was to compute any one of these expectations, that's exactly what I'm going to get, right? Just say you have m different points, you have m different functions, you choose one uniformly at random. You're going to choose each one with probability 1 over m, right? F of x is your loss function, whatever you're trying to minimize. The question is, what is f of x? F of x is equal to this thing. Yes, this is the definition of f of x. It's just the expected value. There's not like there. Yes, but there's no bias here. That's not relevant. Yeah. Choose I uniformly. Okay, so basically I have m different points. I'm just going to choose one of them uniformly at random, right? On average, what is my gradient? Well, it's 1 over m times the gradient at each of these points, right? Which is exactly the gradient of f of x. Right? So on average, the direction I'm going is exactly the direction of my gradient. Okay? Does that make sense to everyone? Okay. So how much time do I have? Oh. Okay, so what should I tell you in 6 minutes? There's a lot of stuff I want to tell you. Okay, so let me just tell you something high level, and then I'll get into details next time. So what stochastic gradient descent is saying is that instead of taking the whole gradient, take one step at a time. Stochastic gradient descent is harder to prove convergence of. Proving convergence of it is kind of out of scope of this class. We're not going to do it, okay? What I will do for you next time is I will do an example of how stochastic gradient descent behaves in the case of least squares. The thing to know about stochastic gradient descent is most of the time what you will do when you're using stochastic gradient descent in practice is you will choose a decaying step size. So unlike gradient descent, where you always have a constant eta, here you will have an eta that depends on time t. And as t gets larger, your eta gets smaller. It's one way of kind of forcing convergence, right? In gradient descent, you get convergence because your gradient itself goes to 0 at the minimum. Here, because you have all this randomness, you might not have that happening, okay? So you force that to happen, especially for some of the convergence proofs, by essentially getting eta itself to go to 0 as time goes on. So you're kind of forcing your algorithm to move less and less and less. One of the things that stochastic gradient descent will do, and one of the reasons that it's used so widely, is that it can be very helpful for getting out of these local minima type situations. Because instead of following exactly the gradient, it might do something kind of noisy, right? And instead of going exactly down that like straight good student path of exactly to the minimum, it might say like, well, I'm just going to jump over here, right? Even when the gradient might be pointing in a different direction. Because all you're doing is on average you're going in the right direction, but you know that might be sometimes you're going this way and sometimes you're going this way, even though your average direction is this way. And so that's why basically stochastic gradient descent is useful for getting you out of these local minima type situations, okay? And then there's lots and lots of different variations that build on top of this. We'll talk a little bit more about this in the next class, but I guess I'll stop here. I have 3 more minutes. Okay. So what I'm going to say is that this is the last lecture before the midterm. Gradient descent is in scope for the midterm. We're not going to ask you about like strong convexity and smoothness, the stuff that I only introduced today. Like kind of the extent of gradient descent that is in scope is what we introduced in the last lecture. I hope you all attended the review session. Remember, the most important thing for you to do to practice for this midterm is to make sure that you understand lectures, discussions, and homework. That is way more important than doing any kind of practice problems, any kind of thing that someone on Reddit tells you about. Guess who knows what's on the exam? There's one person in this room.
You.
So whose advice should you follow?
You.
Good job. Okay, I will see you on Monday.